In this video, we look at cylindrical shells, the concept, just the idea behind it, and the derivation of the formula. Sometimes when you're trying to find the volume of a solid of revolution, it'll be impossible to do by disk and washer, or disk or washer, sorry. Here's an example. Let's take the function y equals the sine of x squared. Okay, the graph of it looks like this. I wouldn't expect you to draw it. You wouldn't have to know this. And let's say we'd like to revolve this around the y-axis. Okay. So there's a discernible gap between the region and your axis of rotation. So we would think about trying to use washer method. Remember, washer method requires you to find an outer radius and an inner radius. The outer radius goes from your axis through your region to the outside curve. And then the inner radius goes from your axis up to your region and its inside curve. What's the issue here? Well, there are a few issues, but one issue that probably ends up as being the most problematic is the fact that if we were to do washer, it would be in terms of y. These washers, when we rotate, will end up laying on their sides, and we'd have to move from some low point to some high point. And so we'd have to solve for x in terms of y. Not that it's undoable to solve for x, but what you get out will be something that will end up giving you trouble when it comes time to integrate. We take the inverse sine of both sides, and then we take the square root. So x is equal to the arc sine of y underneath a root. We do not need to, end up trying to figure out how to find the antiderivative of that. In fact, we can. But the bigger problem is the fact that the outer radius and the inner radius are going to the same curve. This distance off of the y-axis is x. And so they both are going to x equals the arc sine of y underneath a root. And so if we were to set up washer, we would have an issue because of that. We need another technique, and so what we need is something else. And so that's where shells comes along. I mean, shells doesn't only work when disk and washer doesn't, but this is the motivation that we have for it. Let's take a look at the method of shells. So there's going to be a series of nested cylinders. Okay, we're going to try to find the volume of the solid of revolution by considering these nested cylinders. Okay, so in this slide we're going to go through some intricate steps to derive the formula. If you don't understand what's going on in this slide, that's perfectly fine, but I feel it's necessary to talk about it so that you can get a feel of what's behind the actual formula. So here's a shell, and the shell has a height and a radius. Okay, and what we think about it is kind of like with the washer. There's we're going to think about this as an inner shell and an outer shell. Okay, we have an inner shell with the radius represented by the blue distance, an outer shell with the radius represented by the red distance. And what we're interested in is the in-between. Basically the kind of like the donut or region. The shell could be found basically by trying to take the volume of the outer shell and subtract from it the volume of the inner shell, the inner cylinder, sorry. The volume of the outer cylinder minus the volume of the inner cylinder will be the volume of the shell. Okay, Great. So we're talking about cylinders and volume. Volume of cylinder is pi r squared h. So the volume of the outer will be pi times the radius, that's the outer, squared times h. They do have the same h. So the volume of the inner will be pi times the inner radius squared times h. Both of these two terms have a pi and an h in it, so we'll factor it out. And we'll be left with this difference of squares, the outer radius squared minus the inner radius squared. So let's exploit that by actually just writing that out. You know, a squared minus b squared is a plus b times a minus b. So let's think about it like that and have it as outer plus inner times outer minus inner. Right, a plus b times a minus b, the difference of squares, factored out. Okay, now we're going to get a bit creative here, but just bear with me. What we're going to do is multiply and divide by 2. That way we're not changing anything, and here's the reason why. The outer radius plus the inner radius divided by 2, this term here, that's like an average radius, right? You add two things up and you divide by 2. It's like an average. Okay. And so let's just call that average radius r. It's the radius that'll take it in between the two, the average value between the two. So we'll just call that r. And then this difference between the radii, we have this outer minus inner term. We're going to call that the change in radius. It's the delta r. So this formula for the volume of the shell, this particular shell, will involve taking 2 pi r, that's this part here, outer plus inner divided by 2, times h, times delta r, that's this part here. 2 pi r should look familiar, that's the circumference, h is the height, and then the thickness is delta r. So this will give you the volume of this particular shell, 2 pi r, h, and delta r. Now what are we going to do with this? We're going to have a series of these. We say they are nested, one inside of the other. And so then we're going to take the volume of the one particular shell and then add to it the volume of other shells that are nested inside of it, and then eventually we'll end up with some approximation, which later we can make better by making the number of the shells go towards infinity. Let's take a look at it. So we have the volume of the shell. Here's a picture of it, a static picture of one particular shell. And we have the formula from the other side, 2 pi r h times delta r. Okay, this is a typical shell, so we call it on a typical interval. So we're going to take this interval from some a to b, chop it into subintervals like we normally do, and call this typical subinterval that we're at xi. And then the endpoints of it are xi minus 1 and xi. And then in the middle somewhere we'll call it xi bar. That's kind of like the average, you know, maybe it doesn't have to be exactly in the middle. It's just like our xi star from previous. We choose some place in the interval to do our evaluation. Okay, and what we need to do is call that distance xi star. Sorry, it looks like it's a little bit past here. This is, remember, y is your axis of rotation. So this distance from your axis out to this typical rectangle is going to be called xi bar, and that's the radius. The height of this rectangle is the function evaluated at that xi bar. So we just go up here, figure out how tall it is, and that'll be how tall the shell is. So we have the height being f of xi bar and the radius being xi bar. We can plug those into our formula. And instead of delta r for the thickness, we can call it delta x. This is the volume of this ith shell. What are we going to do with this? Well, we're not going to move to the next interval, the next interval, the next interval, and we're going to add up the volume of some finite number of these shells. And it'll be an approximation to the true volume. So we take this ith shell, we throw it into the formula, and we sum up. There'll be n of them when we chop our interval into n sub-intervals. But we've seen this before. This is going to be as accurate as we like. In order to get more accurate, we will then have to think about letting the number of sub-intervals go to infinity. What happens when you do that? You're going to get a better approximation. So we have this limit of this sum. Hopefully this looks familiar. This is a Riemann sum. And now we no longer have an approximation. We have exactly the volume. So now we have an equal sign here. And this is going to end up as an integral from a to b of 2 pi x for xi bar, f of x for f of xi bar, and delta x becomes dx. Now this isn't the formula that's always going to be the case. Okay, this is this particular instance when we have the region that we're rotating being underneath the curve f of x and above the x-axis, and we rotate around the y-axis. In this special instance, this is actually the formula that you're going to use. Okay. It won't always be this, though. So we need some general formula that'll help us through the problem. And it really is based off of our generic kind of shell volume that we derived on the previous slide. Okay. So in general, what we're going to have is, in place of this x, what does this x come from? It's the radius. In place of f of x, where does f of x come from? It's the height. So generically, it's going to look strange to write it like this, but I want you to think about anytime you go to set up the volume of a three-dimensional shape, or the volume of a solid by shell. I want you to think about this particular integral here. 2 pi times the radius times the height. That's going to be what you integrate from some a to b. It won't always be in x. We'll see that sometimes it might be in y. And how do you know what the radius is? Well, it'll change depending on the problem. But just like with disk and washer, when you have the radius, what it is a distance from the axis of rotation, and then we're going to have it to some typical rectangle. So we're going to start off by drawing a typical rectangle and go from that axis to that rectangle. Remember, that's what xi bar did. It went from the axis here to the typical rectangle. Okay. All right. And then what's the height? That's just the height of the rectangle, basically. It might not always be f of x. And the integral might not always be dx. So how do you know when it's going to be dx? How do you know when it's going to be dy? Well, basically it's going to be dx if you have a vertical axis of rotation. It's going to be dy if you have a horizontal axis of rotation. Okay, this chart below will help us keep the methods separate. You see, in every problem now, when trying to decide between disk, washer, or shell, I want you to start by drawing a typical rectangle. Okay, and they're drawn differently for disk / washer versus shell. For disk or washer, when you draw your typical rectangle, they end up being perpendicular to the axis of rotation. While for shell, when you draw your typical rectangle, it must be parallel to the axis of rotation. Okay, let's take a look. So, say you have a vertical axis of rotation. Okay, and you draw a typical rectangle perpendicular to it. So when you go and spin this around the axis, you'll get a disk Or if there's some gap between it, you'll get some sort of a washer. Okay. So what variable will this be in? Well, your disc or washer will be laying on its side, not standing up and down. So when it's laying on its side, your integral is in terms of y. So it's a dy integral. Okay, that's if you're doing disc or washer with a vertical axis of rotation. Now when you're doing shell, you have the same vertical axis, but then you draw your typical rectangle parallel to the axis of rotation, and you just have to visualize this thing moving about this axis of rotation. You end up with a shell and not a disc or a washer. But this time, what happens is the typical rectangle standing up and down. And so with this situation, your integral is going to be in terms of x. Okay? And the flip of that is, okay, now let's look at a horizontal axis of rotation. For disc/washer, your typical rectangle you should draw would be perpendicular to the axis of rotation. And visualize it being spent around that. You'll have a disc or a washer. But now your disc or washer will be standing up and down, and your integral is going to be in x. While for a horizontal axis with shells, you draw your rectangle parallel to the axis of rotation, and you go and spin it around, and you definitely get a shell. But now your shells are laying on their sides, not going up and down, but kind of going left to right. And so then, in that case, your integral is going to be in terms of y. Okay, so this is just a sort of cheat sheet kind of ready chart here to help you figure out between the different methods. Disc and washer get thrown. It should be disc. It says disc or washer, but they're thrown in together. They're really the same thing. Washer's just disc in disguise, and then there's shell basically. And so when we're trying to decide between the methods, we'll draw the typical rectangle, we'll draw the axis, and then we'll match it up and figure out which one would be best for us to do. It won't always be the case that one method doesn't work, so you should always try this other. It could be that one method will work and the other method will also work. And so it's just a matter of finding the one that works best for you. I'm going to end this video. No calculations in this video. This is just the concept. I'm going to end this video with a visual. Let me escape out of this for a second. And 1 second. Okay, so this website here, give credit to have to give credit to the professor. He's from Temple University. He created this this website that has these nice videos that instead of using my static pictures, you actually get to see the shells being created and nested. Let's go with a couple videos here. Let's see what happens when I hit this. Okay, QuickTime movie starts up. Okay, so what's happening is you have this region that you're going to rotate. Looks like you're going to rotate around the y-axis. So you're going to chop it to some subintervals, and then you're going to take a typical rectangle and rotate that around. And what you're going to see is just a half view of it for now. Then it's going to keep coming around. That's how we're going to get a shell. Well, why do we say nested shells? It's going to be because you're going to have they're going to be one inside the other. When you go and rotate these, here's the half views of the rotation. They're going to continue to go around, just let the animation go. And so there are these nested cells, one inside of the other, like the Russian doll. Okay, nested shells, kind of like what's that snack? Combos, right? Okay, so that's the approximation. This region gets revolved, and we get an actual solid. And it's our job to find the volume of that solid, and we get the visual of the nested shells. Okay, let me do one more for you. Maybe I can make it larger. I don't know. Yeah, I think I have to download it. But anyway, here we go. So this is the region between two curves. Looks like y equals root x and y equals x squared. That gets rotated around, once again, the y-axis. Sorry, I could have picked one and did the x-axis, but here's a typical rectangle, parallel to the axis of rotation. We revolve that around and we get this shell. Okay, but there's a series of nested shells. So we'll go back and revolve each one of these guys. And right now we're looking at only the half view. And then we notice that you get the following kind of shape. This is the approximation though. And to get the exact value, we use the formula. So I just want you to see the nested kind of cylinders. And that's an approximation to the volume. And the actual volume is generated when this shape gets revolved around, has the smoothness to it, and we find the actual volume by integrating using our formula. And so that's the concept behind shells. It took a little longer than I wanted, I apologize, but hopefully it's understandable, and now we can look at some calculations next.